Ken, for having us. Really happy to be talking here at the Go. So quick note about who we are and what we do. So we're from Arktos. Arktos is a new startup in the Menlo Park area. We're a data analytics tool, and we're working on building a layer of analysis that sits on top of web APIs. It lets people ask questions using search, natural language, about whatever data they have coming through web APIs. And to do that, we've been using a lot of Go. Our backend is written almost fully in Go, and we've been building a lot of infrastructure on our end in order to make that happen. That infrastructure varies from things like, on the natural language processing side, context-free grammars and parsing tools, to things on the data handling side. We're working on building a query language that we call ArcLang, which we use to actually construct database queries against these APIs. We're also working on building an ORM, which we're using to actually define all of our object models, and that's how we persist data in our system. So the talk was originally going to be focused entirely on how we use SQL in this ORM, but we decided that it would be more beneficial for everybody to do that, as well as talking about the ORM in general and some of the other tools that we built in order to support our web application backend. Yeah, I'll let Ted take it from there.
Solid. Let's get started. Okay, so we're going to be talking about scaling a Go Codebase and some of the things to keep in mind when you're looking to grow a web application written in Go. So things like type safety. Actually, let's cover our needs first. So basically, we're building a web application that we expect to be around for a long time. Like a good rule of thumb with a startup code base is to expect code that you write to be around for half of the lifetime of the code base. So if you write code and you're like, all right, this is great, this is kind of a hack, I'm going to redo this in like 3 weeks, I'm going to come back to it and revisit it. It's entirely likely that that will get shoved aside in favor of new feature development, and 4 years later, you'll find a comment to yourself that says, if you're reading this function finally broke and you hit that one race condition, sorry, bro. Yeah, so we would prefer to avoid that. And we think there are a number of simple initiatives we can take early on to prevent ourselves from kind of digging ourselves into an architectural hole. A number of principles for maintainability. So we're looking to counteract two main pain points that both Ryan and I have dealt with. We are former Rails devs, and we absolutely love Ruby on Rails. One thing that Ruby on Rails does that's not idiomatic to Go is it's very magical, which is very convenient. However, in Go, it's difficult to build up the abstractions to support something magical while keeping type safety and keeping things what we call maintainable. So if you have abstractions that make you wonder what's going on, that's not a terribly good long-term indicator for a Go code base. And then also repeat code at the application controller layer is a problem that we were running into early on that we took some steps to counteract architecturally. So for us, maintainable means maintainable code is easily extended, which means that you can add new anticipated functionality. So a maintainable routing layer for a web application, for example, lets you add web endpoints with very little overhead. It's not this ordeal of writing a function and trying to figure out where to plug it in to get the route to fire properly and trying to get all the middlewares lined up properly. The idea is that maintainable code lets you extend the functionality in a very predictable, very low overhead manner. Maintainable code is dry. You don't repeat yourself. Meaning that if you write a function that does something like check authentication on an HTTP request, you shouldn't have to put those 10, 20, 40 lines of code in every single route that requires an authentication check. You should be able to abstract that into middleware, which fires every time you make a request. Maintainable code is type safe. Static analysis is for all the obvious reasons, crucial in a Go code base, which means that overuse of things like the reflect package can really not only damage your performance, but just damage your ability to really know what's going on and damage your ability to kind of grok at a glance how your code actually fits together. Minimal code bottlenecks is another important thing to keep in mind when designing a web system. So a routes file is a good example of this. If I have a bunch of developers working on different features for an API, each one working on a different set of endpoints, they all have to modify a centralized routes file to add that functionality to the API. and it turns into merge conflict hell. Ryan spent some time working at Facebook, and he can speak for for the Facebook routes file. It's a single file of PHP with just like what, thousands?
Yeah, it's huge. I mean, when you're first starting off, your routes file is probably going to have maybe a couple dozen routes defined, but pretty soon, like over time, it grows quickly, especially as more and more people are adding features on top of your API. Facebook's route file has dozens of merge conflicts a day, and it's a pretty significant bottleneck in terms of actually resolving code. I'd say that when I was just building new features, the amount of time that I spent resolving routes file merge conflicts was just completely ridiculous.
Yeah, more than it should be, right? All you want to do is add a simple feature. You shouldn't have to worry about accidentally deleting 3 other teams' features because you're trying to add yours. I mean, merge conflict resolution isn't that hard, but if it happens often enough, somebody is going to mess up eventually. And then also, testable code is important. So this means keeping things modular, keeping settings self-contained, avoiding global config patterns that can easily cause import cycles. Yeah, let's talk about the ORM.
So specifically when we started building the ORM, we noticed that there are a few problems with the ORMs that are available in the Go world. First, it's worth noting that the ORMs that exist right now are in pretty early stages of development, which makes them it makes it understandable that there wouldn't be a whole lot of functionality. And we thought that was a great opportunity for us to be extremely opinionated about how we would go about designing the optimal ORM to suit our needs. Some of the problems that we found in the ORMs that existed were that they weren't type safe, and that they required you to infer a lot about the models that you were storing. They weren't immediately comprehensible, which means that there was a lot of magic going on behind the scenes that was preventing us from being able to really understand how different parts of the ORM were actually doing their jobs. And the reason why we thought that was bad was it makes it easy to create new models, but when you decide to do something fancy, then it's really hard to learn more about how a system functions. And so that's what we mean when we say it's not easy to build on top of. It's one thing if it's really easy to add 10, 20 new models. It's another thing if you decide that you want to be able to extend the system so that you can have pre-save hooks or something like that, and the ORM doesn't natively support that, and you have to hack it together.
A good example of that is, so some of the ORMs out there right now for SQL will introspect a model. They will look at the name of the type using the reflect package. They'll store it in a map, mapping an object of that type to the name of the type as a string. So if I have a type called user, then that'll get stored in a map of an empty user object to the string user. And then that string becomes the table name. You yourself don't define the table name by default. There is the option to for many ORMs, but we consider that slightly problematic just because it causes a lack of transparency, causes a lack of understanding what's really going on under the hood. So later, if you want to write a scraper, for example, a delay job which goes in, grabs stuff out of the database, aggregates it, and then sends you an email report, for example, you don't know what the column name is. And it's not terribly easy to find out without going into the database and examining the schema, rather than an explicit declaration of, hey, we're going to store this field in the column called this. Hey, we're going to store this model in a table called this. Without that explicit declaration, we found that we could figure out what was going on, but it was just a little more effort than we would like to put in. We would rather put that effort in up front when we were developing the model than put that effort in trying to extend the model later. Cool. So this actually kind of relates to, actually who here is familiar with the web framework Martini? Awesome. Martini is a great framework. The creator of Martini actually put out a blog post some time back where he said that although he was very proud of Martini, he considered it to be unidiomatic Go because it uses reflection a lot and because it obfuscates purposefully from the user for convenience's sake what's actually going on. And then he released a much simpler package called Negroni, which is a great middleware package. This is kind of along the same lines of that. We had the option to, and we certainly could have built a SQL interaction system using existing ORMs, but we felt that they were less idiomatic because they don't let the user explicitly define the way in which the Go code is interacting with the SQL database.
So here we're going to show you an example of how our ORM actually functions. The top level of that ORM is actually the model interface. And so these are the methods that each model needs to implement in order to provide the information that the ORM needs to be able to connect and interact with the SQL database effectively. We'll give you an example of a model so you can see exactly how this works.
Great. So this is a user model. Here we have some fields on the model. They have JSON tags for easy serialization. And then there are some methods defined on user which satisfy the interface from the previous slide, the model interface. So here, for example, we have user returning a string on the method table, and it just says users. Really straightforward, doesn't change. The string users is the table for all users, all instances of the user type. Below that, we have direct access to all of the values of the user's fields at any given point. And those are connected to the names of the columns in the user's table. So instead of guessing which column, which value is going in, instead of doing name manipulation under the hood, here it was our choice just to make it explicit, the relationship between which column values are being persisted to and the value of the persistence. So the other two methods in this basic model interface, this is kind of a simplified version of what we're using, is the insert columns and update columns. These just basically say, okay, here are some columns you can insert into the database, and the ORM knows what to make of this. And then the update columns say, okay, here are the columns that you can update once a model has already been created. The reason that this is important is because it lets you make certain columns immutable from the application layer. So if you define a specific slug for like a blog post, for example, or like kind of like Cloud App does specific short code, you probably want to make that immutable because it has to do with data persistence and just data integrity over time. Here's a more complicated example.
Cool. So this example is a little bit more complicated because it uses a password on the user. And it gives you an example of how we might build on top of this model to provide additional functionality. So imagine that you had a user model and you wanted to be able to take in a plain text password when the user is created, but you wanted to hash that password and then store that hashed password in the database. You wanted to create basically a before save hook that automatically hashed the password when the user was created, so you didn't have to do any kind of hassle when you're actually writing the creation code. So this describes the password and the password hash fields on the user struct. Then the only change that you see here in the update columns is that the password hash is added to the update columns, but not the password, because we don't actually want to store the password field in the database. That would be bad, because then plain text passwords are everywhere.
Yeah. There's also a lifecycle hook right here, which basically just says before you insert the user, hash the password and persist that instead. So here we could just unmarshal straight to a user object, and then the pre-insert lifecycle hook would run. It would hash that. A couple benefits also of the models themselves providing direct access to their fields means that you can create private fields on a type, and you can make those accessible to the DB even though you don't want them accessible to other packages. Just another thing that helps with maintainability. Defining a proper API and only exporting what you need to export, what needs to be accessible by other packages.
This is one more example that provides an additional use case of extending functionality. Specifically, this is creating a dependency between models. A way that you might actually use a dependency between models is, let's say that you have a user model and then you have a comments model. And users have many comments. And you want to tightly couple the relationship between those two things, such that if you destroy a user, it also goes into the database and destroys all of that user's comments. So you don't have vestigial comments that no longer belong to anybody living in your database. So one way that you might do that with our ORM is you might define that on the user model, a list of dependencies. Specifically, as dependents, you would say that the comment model maps to a particular join structure. The reason why this is important is because it allows you to explicitly define the relationship between the user and their comments. So here it says that the field on the comment that you care about is called ID. And the field on the user model that you care about is called, or or the field on the user model is ID, and the field on the comment model that you care about is called user ID. This allows you to explicitly define the relationship between those two things. That's useful because there are many cases in which you have multiple possible polymorphic relationships between different models. For example, you might have a user related to another user as, say, a referrer, or you might have different kinds of relationships between users and comments. And so this would allow you to explicitly define the nature of those dependencies and allow you to control when those dependencies cause cascading deletion and when they don't.
Awesome. Here's some example usage of the ORM. It's pretty straightforward. Just create a user model from the package models with the set fields, and then very similarly to, the user interface is pretty similar to other ORMs out there. It's really just under the hood what's going on that's significantly different. So you say error db.create, pass in a pointer to the user. It's pretty straightforward stuff. Here's the retrieval of a user on the bottom. Awesome.
One notable departure that you'll notice from the actual usage syntax of this ORM to something that you might be used to in a different language, like say Ruby or Python, is that we're not calling user.create or user.update or user.save or anything like that. And the reason why is because in order to keep the ORM dry and also maintain type safety across different models, you want the actual ORM functions like create, get all, things like that. You want those to be top-level functions that accept in a model, where a model is the interface that is implemented by user, by comment, etc. That allows you to ensure that you're always working with a user model or a comment model, and you can keep the code dry at the same time, defining exactly one create function for the entire ORM, one get function for the entire ORM, etc. It's a usage pattern that's pretty common in Go that you won't see in other languages. So if you're new to Go, that's something to pay attention to.
Yeah. Also, completely type safe, as mentioned, which is just useful if you have a function on a model that returns a different type of object, and you believe you're passing in one type of object to a database insertion. It will catch it statically instead of waiting for you to find out at runtime, hey, you're actually passing in something which you haven't given instructions to be in the database. Awesome. So that's the ORM. The second thing we'd like to touch on is some of the middleware compositional stuff we did as far as putting routes together for the web application. So there are a lot of middleware solutions out there that let you define blanket middleware for a collection of routes. So you can say things like, all right, for the entire application, every time an HTTP request comes in, log it to this file right here. You can say things like, okay, for the entire /admin block of routes, check to see if the user has a token in the header. If they do, let them through. If they don't, 401. However, one thing that was notably lacking is the ability to compose Go code at the route level instead of the group of routes level. What this means is every route in a chunk of routes, like let's say /users, would have to repeat code inside the controller logic to get set up for whatever action it needed to perform. So the essence of the post to /users route, or actually let's say the essence of the update /users/ID route is to fetch a user from the database, overwrite some values, and then write that user back into the database updated. What that requires is parsing the URL to turn a user ID into a number, and then using that number to extract the user out of the database. Pretty simple stuff, and that's pretty common to other routes like the delete /user/ID or get /user/ID. That code shouldn't have to be repeated. You should be able to write that once and then let it run for all of the routes that have an ID inside the URL. However, not all of the user routes have an ID, only a few of them do. Post to /users, for example, doesn't have an ID. It wouldn't make sense to say post to /users/ID. You've already made a user, they already have an ID. What are you doing? So the point is that right now, a lot of middleware solutions don't let you define middleware for only specific routes. So you can't drop a blanket solution that says extract the ID from the URL, parse it, and fetch a user from the database on the whole chunk of users routes, because only some of them have that ID in the URL in the first place. If you say extract this ID, it's going to fail sometimes. So we had this idea of letting ourselves compose controllers through a combination of setup middlewares. So for a certain controller, we could say, okay, extract this ID, fetch from the database, and then proceed only then to the custom logic, which we put inside a traditional HTTP handler func. Awesome. Yeah, fine-grained middleware.
Yep. So we're going to show you a very brief example of what that looks like when it's actually implemented, so hopefully you can appreciate the simplicity of the solution. So just some overhead that we need to know about are these types that we've defined, specifically for the notion of a route and the notion of a route collection. So a route has a handler which defines what's actually happening when that route is hit. And it also has a slice of middlewares. Well, middlewares are also handler functions that are evaluated in linear order and are composed within each other. That allows you to basically set up the handler that is actually evaluating, that is being evaluated at that particular route. A route collection groups a bunch of routes together and defines middlewares that should be applied to all of them. Yeah. This is an example on if you go back just one. The only admin is just an example of a middleware that you might use. So here's an example of an actual route. So one thing to note here is that the actual definition of the route, so the path of the route, is defined at the top inside of the helper function that we call register. All that's doing is it's saying, hey, tell the router to be aware of this particular route. Note that the actual path is defined in the same file as the actual logic that is being carried out as a result of hitting that particular route. The reason why we think that this is a good practice is because it avoids the code bottleneck that we talked about at the beginning of the talk, where you have one central file where all of your routes are defined, and instead your routes are defined closely coupled with the actual logic that they're associated with. Now, you might think that it is valuable for a developer to be able to see all of the routes in one place, and we agree, but we think that that can actually be easily accomplished by just writing a utility that goes in and manually aggregates all of the route files into one place and shows you a list of all of the routes and what they do. That is preferable to slowing down development by forcing people to decouple the actual route definition from the logic that's associated with their action.
Yeah, this I don't know. It's a departure from a pattern that we've seen in several open source code bases that basically have one API file that's 1,500 lines long, where people just have a single map of routes to HTTP handler funcs. And we didn't really like that approach. We feel that this gives us the ability to work concurrently on multiple branches of the API at the same time and make it really seamless to integrate them. Less developer overhead, however, incrementally. So the end point of the talk is that there are certain steps you can take to make your code base more maintainable early on, little architectural decisions that add up over time as far as saving developers time and effort spent debugging or resolving merge conflicts. And that's important because in the long run, speed of development really equals how maintainable your code base is. You can use the reflect package and save yourself time in setting up a database. You can save yourself time in development early on. But if you put the time in as an investment into making sure that everything is type safe, everything is readable, everything is explicit, it's going to lower the onboarding cost of bringing on new developers because they don't have to hunt more than 2 or 3 layers of abstraction deep to find out what's going on as far as database interaction. They can find out what's going on at the route aggregation level pretty easily because there's no magic going on under the hood. All the files are separate, they're grouped by category, they're grouped by API resource. And just like in the end, if your code is more maintainable, you're going to find that you spend less time debugging and more time actually developing features. The infrastructure is an investment.
Cool. We'll take questions now, in case you guys have any thoughts or responses to some of this stuff that we've shown you. Yeah, question in the back.
Did you guys look into using struct tags like the standard library does instead of your like columns function? Like, it seems like struct tags columns single.
It's on the radar. This was the initial version, like the other ORMs, actually more like the other ORMs. Our ORM is very early on in development, so we have an agenda of things that we can do to improve it. You noticed it's pretty verbose right now. That's something that we're willing to trade off because we think that making that explicit is really helpful. But there are certainly other ways to make it explicit that would cut down line count. So that's a great suggestion. Yes?
So, yeah, I'm wondering in your early design phase, if you considered a design that is more noun-verb and less, let's see what I can say. You can have a center of gravity that's towards the ORM declarations, and you can have a center of gravity that's towards the database implementation, and there's ways to write both of those things.
Sure.
And I'm wondering if, for your own thinking, just your personal taste and
Definitely.
constraints, if you considered more of a noun verb and then encasing things that were closer to the database in code, including in SQL, in name tonight, and rather than more sort of the Rails style or more of the center of gravity towards the declaration in the ORM, if that makes sense.
What would an example of a design pattern that gravitated towards the database be?
So basically,
Just to make sure I properly
in
understand.
days you can say, you have a universe of nouns, and then you start to declare verbs that are associated with those nouns,
Sure.
and the logical relationship and code paths that come from that are in the realm of the code, but then at the time they go to get executed, it's something that is fairly database specific, and that's called a sort of an atom. Instead of having the code essentially declaratively compose the SQL that's going to get executed.
Right. So the truth is we didn't put a whole lot of thought into that. We prefer, at least I can speak for myself, I would say I prefer the style of ORM management that gravitates more towards the application level, mostly by merit of familiarity. So that's why we ended up going with more of a Rails style approach, as it were, modified to fit Go idioms. Yeah, but it's certainly a spectrum, and there's certainly a way to apply the principles to writing a database-centric interaction model. Thank you.
Any other questions?
Yes, what's up?
Yeah, so your earliest slide there was something admirable. You were saying you're trying to repeat code, which I guess you mean by boilerplate.
Yes.
So on many abstraction layers, and I think you're saying it's many abstraction layers can kind of do well. Those two goals can kind of pull you in different directions, right? One of the reasons we have abstraction layers is to remove boilerplate. Would you agree with that, or did you find that different there?
I certainly agree. I think they do pull you in different directions, but perhaps, I believe I specified actually, for us, we were finding the abstract, let's see, in the goals I believe I state, we're looking to minimize repeat code, especially at the web controller layer.
Okay.
Yeah, so that's where we were running into a lot of problems with repeating database fetches or authentication checks, for example. But as you can see from the ORM, we're not averse to putting lines of code into being explicit about how we structure our data, because that's an upfront investment, that's a fixed cost, as opposed to the variable cost of reading all the controllers, which is probably where we're spending more development time right now.
Yeah, I think in the process of system design, you find yourself making design decisions that address trade-offs exactly like the one that you just described. Abstracting code certainly makes it easier to keep it dry, but there's a point, I think, where it becomes so abstracted that it's harder to actually use and build on top of it. And I think the phrase that we like to use is that it makes you wonder what's going on. And we'd like to avoid that in order to increase code maintainability. Yeah, question?
Last couple of months we see many libraries on GitHub which use code generation, and it's overpowers libraries which use just type reflection. For example, JSON overpowers standard library JSON, and message pack is fastest serializer on Go now, which use code generation. What do you think about code generation and writing ORMs?
So the verbose model right now lends itself towards code generation in the sense that we could do kind of, if we really wanted to, I suppose, we could do what Rails does, where it generates a new file for the model, has the boilerplate, has all the methods in the interface spec'd out for you, and then you just go in and fill in the columns or whatever. That's assuming we don't adopt the excellent suggestion about the tags on the struct. Code generation is certainly useful, especially when you have a schema into which you can generate things. I'm not sure we have specific need of it right now. With regards to ORMs, I suppose it depends on how magical the ORM is. I would say there's an inverse relationship between how magical an ORM is, meaning type inference through reflection, and the usefulness of code generation. Because if you're explicitly declaring templates, or if you're explicitly writing code that fits kind of the same mold time and time again, then it would make sense that you would want to kind of automate away the process of generating that code. But if the ORM is picking up everything for you, I would say there's not as much use for it. That's my intuition. I haven't done a lot of thinking on the subject, but. Awesome.
Sounds good. Well, thank you all for your attention. Just to wrap things up, Arktos is hiring Go developers. And
Shocking.
If you're excited about building stuff like this, or if you're interested at all in data science, data analytics, building a natural language tool for asking questions about data, then you should absolutely get in touch with us. Thank you all.